Alrighty, good morning, lads and ladies. Welcome back. Excuse me, sorry, my wife brought me some pineapple. Today we're going to talk more about applied optimization. Talk a little bit about the test structure, stuff like that, and then solve some more optimization problems. I'm also okay with solving some other problems if you guys want. Today isn't formally a review day. That will be on Monday, but today and Monday, mixture of review and exam prep stuff. This exam does cover quite a bit of material. I don't have any problem spending some time kind of helping you guys get comfy and acquainted with that in a sort of all together way, because it's a little bit intimidating. But since the last thing we were talking about was optimization, we only have to solve a few problems the other day. I think it'd be wise to begin there. Also, the details for the test, let's talk about those. So first things first, this is MAC2311, section number OH1, which is Calc 1 honors. And the date today is the 29th of October, 2021. We're going to solve more optimization problems. Other problems of your choosing. And we'll talk a bit about exam 2.
Excuse me?
Yeah.
Just a quick question.
Yeah.
So since I want to take Calc 2 honors next semester, and you're the one teaching it, do I have to do an interview with you again or something?
That is the case, yeah. So even if you're taking Calc 1 honors with me now, if you intend to take Calc 2 honors next semester, we will need to do that same interview process again. The questions, of course, will be different, but basically the same thing. I'll ask you guys anybody who wants to take Calc 2 honors, schedule an interview with me, and then we'll talk a little bit. Obviously, I know you a little now, so we don't need to do the whole getting to know you part of the interview. But we would want to do a little skills test to verify that you're in a place where you can tackle the type of problems we'll be looking at in Calc 2 honors, because they are a little tricky. But then, yeah, normal stuff, regular interview and procedure like that.
Okay, thank you.
Sure, of course. All right, let's talk about the test first. So just in case we missed it, exam 2 is next Wednesday. Which is the 3rd of November. You can take it online with me. And just like test 1, this requires Zoom on your phone, honor lock on your PC, or you can take it at the testing center. There's no you don't need to make a reservation or request. Just show up. Anytime after 11 a.m. The only little caveat here is be prepared to wait. If they're busy. So they might ask you to wait for a proctor or a computer to become available if they don't have any right when you get there. That's okay. I have a blanket walk-in reservation that I'll make with them for testing for you guys on that day. They'll have the roster. They'll know if who to expect and who not to expect just based on the roster. If you don't show up there, then they'll assume that you're taking the test with me, which is fine. I think they close at 8 p.m. on that day, so you can show up anytime between like 11 a.m. and 5 or 6 p.m. and still get full time on the test. Just be aware if you have a class after this one or other obligations later in that day, and if they are busy, you might have to wait a little while in order to get started, which could eat into some stuff that is outside of our class time. The sections on the test. I think I might have done this the other day, but okay. I think we start at 3.9. Let me triple check here. Anything, I'll get to your question in just a second. No, sorry. So second on the test start at 3.5. 5, 3, 6, 3, 9, 3, 10, 3, 11. 3, 9 was implicit differentiation. 310, which was logarithmic differentiation. And derivatives of log. I'm sorry, I said 3 9. I'm so stupid. 3 5 and 3 6. I don't know where my brain is. Sorry, 3 5 and 3 6. And then after that was 3 9, right? Yeah, because we skipped 3 7, 3 8, 3 9, which is related rates. 310, which is linear approximation and differentials. And then we jump to 4.1, I think. Right? Oh no, 3.11, which is hyperbolic functions. And I do want to make a little note here, just the definitions. And regular derivatives. All right, so I'm not going to ask you any questions about the inverse hyperbolic trig functions, just the regular hyperbolic trig functions, the definitions of those functions, and the derivatives of those functions. So I'm not going to stress you too much on the applications here or anything to do with the inverse hyperbolic trig functions. Then we jump to 4.1, which was on mins and maxes, specifically absolute mins and absolute maxes. And then we had 4.2, which is on the mean value theorem. 4.3 on derivatives and the shape of the graph. 4.4 on L'Hopital's rule. 4.5 on curve sketching. And then 4.7 on optimization, right? 4.6 is calculator stuff. It's 4.7. So these are all the sections that are on the test. And it is quite a lot, right? It's a little more material than is on exam 1. Exam 1 was all of chapter 2 and the first half of chapter 3. This is like the second half of chapter 3 and pretty much all of chapter 4. That's applications of the derivative, stuff you can do with the derivative. Places I would put a little star here. Indicate that it is exceptionally important. Would be like these guys. Right, I would say if you understand 4.3, then probably you're comfy with 4.1, right? This is sort of implicit in here, as is, you could say something similar about 4.5, right? If you understand 4.5, then you understand 4.4, 4.3, and 4.1. Folks sometimes struggle with implicit differentiation just because it's like the first topic that we covered after exam 1. It's been a little while, so you might want to go back and make sure you're really comfortable with implicit differentiation, using it to find tangent lines and stuff like that. Related rates and the optimization section, those two applied sections where you have to think quite carefully about applications, can be a little bit tricky. Curve sketching problems, these take forever, right? You guys have noticed that. A single curve sketching problem can take 20 minutes if you're not really efficient about it. So make sure you practice enough of these that you can move quickly through them. And then 4.3, if there's one section that really checks how well you understand what the derivative is, and what it sort of tells you about the original function, it's 4.3. So there is sort of an emphasis on this test on section 4.3. Other stuff to maybe take note of here, L'Hopital's rule and indeterminate forms. Certainly the 0 over 0 and infinity over infinity stuff, we all pretty much handle consistently without too much trouble. But make sure you remember what the other indeterminate forms are and how to attack them. So indeterminate products, differences, and powers, especially indeterminate powers. The linear approximation section, make sure you remember just what to do there, right? This is one of those things where if you remember what the linear approximation tool is, that linearization function, L of X, then these problems are very easy. If you forget what the linear approximation tool is, then these problems are impossible. So section 3.10 is one of those where any problem on the test is going to be really easy, but only if you remember the definitions. Those would be my little words of warning here. These are the sections that are kind of well represented on the test. You know, there's guaranteed a problem from each of these sections. And those are the things that people tend to forget or get into trouble with on 310 and 4.4. Any questions about the test?
When you say guaranteed a problem, is like an individual problem about it, or like a problem like with like one problem including multiple?
Well, yeah, the fair question. So a related rates problem is automatically an implicit differentiation problem, right? Every related rates problem requires implicit differentiation. I would say it's quite likely that each section with a star here will have its own problem. But some of them may be represented more than once. Again, the related rates implicit differentiation thing, every related rates problem has implicit differentiation in it. And similarly, every curve sketching problem has the number lines from 4.3 in it. But I would say you can definitely expect a related rates problem. It would not be an application of derivatives test without a related rates problem. You can definitely expect at least one problem that has to do with the derivatives and the shape of the graph. You can expect at least one optimization problem and at least one problem that has something to do with curve sketching, although maybe not like a whole, here's a function, go through all that stuff. But maybe I give you some information about that function and then I ask you to sketch the graph. Maybe I give you the number lines and tell you to sketch the curve, something like that. Other questions about the test?
Yeah, for derivatives and shape of the graph, you're talking about where we take the first derivative test and or possibly the second derivative test to figure out just behavior of a graph?
Yeah, so like making a number line for f prime to find where you're increasing, decreasing mins and maxes, then making a number line for f double prime to find where you're concave up and concave down and any inflection points. That was the gist of 4.3.
Okay, so if we're comfortable with 4.5, we should generally consider ourselves comfortable with 4.3?
I think that's the case. Yeah, I would say there are no theorems in 4.3 that are not used in 4.5. So if you are comfortable with 4.5, probably good with 4.3, but there are some exercises in section 4.3 that don't show up in 4.5. For example, these sort of things. Remember when we did some of these where I give you some information about the first two derivatives and ask you to sketch a graph that satisfies that information? In 4.5, they give you a function and you have to come up with all this shit on your own. In 4.3, they have some of these slightly more abstract problems where they just give you that information and ask you to sketch a graph that satisfies that. That sort of stuff is a problem type that is unique to this section. But I would say, again, if you're comfortable with 4.5, these problems should be fairly easy, but you may want to practice them a little bit.
Sounds good. From the look of it, they've essentially just given us the number line, but have been very textbooky about it.
Yeah, that's the sort of thing I could do. I could give you the number lines and ask you to draw a graph that satisfies those conditions. Or I could just, another 4.3 problem I could ask you, I could just give you a function, say, find the inflection points, or find all the mins and maxes, something like that.
Okay. Perfect. Thank you.
Of course.
And
Before I
then
get
the
to
other-
Ethan's question, were there any other questions about the test?
Yes.
Yep.
Sorry.
No, you go for it.
So a quick question is, how many questions will you have that'll really be based on like solve this using this method? Because I don't normally memorize formulas by name.
So I promise you, the only questions where I could get specific like that would be 310. The linear approximation where I say, estimate the square root of 1.2 using the linear approximation for root x at x equals 1 or something like that. Outside of that, it really is just like answer this kind of qualitative question about this function or answer this sort of quantitative question about the function. I guess the other place, I should correct myself. The other place there is the mean value theorem, right? I could say find the number c guaranteed to exist by the mean value theorem for this function on this interval. And in that case, you would again, there's a smidge of memorization there. You need to know what the theorem says.
Okay. The reason why I'm asking this is because the test one, I knew what the limit definition was, so I didn't know it by that name. And as a result, I lost 8 points.
I see. Yeah, that's a little savage. Definitely, anytime we call something a theorem, that is something you want to remember. So any theorems from any of these sections are things that, well, I don't necessarily expect you to like recite verbatim. You should be able to describe. So if I asked you, what does the second derivative test say about mins and maxes, you should be able to say, oh, well, I think it says if you've got a critical number and you're concave down, then that's a max, that sort of thing. I don't necessarily expect you to say if f is continuous at c and f double prime is continuous at c and c is a critical number, then blah, 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 like, word for word, but we should at least have the gist of those theorems down, and we should know the theorems by the words that are used in them. I guess another example there would be the closed interval method, right? From 4.1, I could say use the closed interval method to find the absolute max and absolute min for a function. Those are the ones that come to mind right off the top of my head. So linear approximation, make sure you know what the linearization is. Make sure you know the closed interval theorem from 4.1. Make sure you know what the mean value theorem in 4.2 says. Those are the ones that come, yeah, that looks like about it. Differentials are also kind of a formula thing, I guess, right? If y is f of x, then dy is f prime dx. Okay, and Sarah, you also had another question about the test, right?
Yeah, you just answered it while you were describing there. So I'm all good. Thank you.
Okay. And then Yiping asks, so since the test is next Wednesday, what are we doing on Monday? On Monday, I'm going to do a combination of things. We can solve a couple problems in the kind of review style, but I am also going to introduce the material that comes after this. And that brings me to the next thing we wanted to talk about. Let me turn this off real quick. I don't want to show any grade info. We do have a student teaching day coming up soon, right? So where is that?
Yes, it's me. I forgot exactly which one my topic was or the topic number. I know it's with like integrals and like something
Yeah.
related to them.
Yep. So Daniel, I've got you down for 5.4, which is indefinite integrals and net change. So that is a little ways off, but not too far off, right? So if our test is next Wednesday, I'll be introducing the concepts of chapter 5 a little bit on Monday, and we'll cover 5.1, which it doesn't look like anybody's using for student teaching, on Friday. So probably about 2 weeks from today, I would expect us to get to 5.4. So we should have a couple meetings before then. This is a somewhat tricky section, and I do want us to have at least 2 meetings. One meeting to kind of discuss how you intend to do things, and then one meeting to go over the clear nuts and bolts and look at exactly what you're going to present and how you're going to present it. So if you could email me about that or Canvas message me, we can make those arrangements.
Yeah, I can do that. Are the meetings like, is it during the office hours, like at a different time?
If we can do it during office hours, that's awesome. If we can't do it during office hours, we'll schedule it for some other time. So I've had some meetings outside of office hours, some meetings over the weekend, some meetings during office hours. I'm not too particular, whatever works best for you.
Okay, I'll send you an email then after class.
Perfect. Okay. Oh, and I see I've got a DM here. Give me just 1 second to reply to that. And then, yeah, so the rest of the class today, we're going to be talking about pretty much whatever you guys want to talk about. I'm happy to look at some problems. We can do whatever you really want to do. I think it would be wise to look at a few problems from a few specific types. There we go. Okay, Sarah, so that's the phone number. Let me turn the screen share back on and we can dive in. So I see there was a request there for some L'Hopital's rule stuff. We can do that. And then I think it would be wise to look at some of this earlier stuff, right? Because we haven't played with implicit differentiation, logarithmic differentiation, or related rates in a while. So first, let's take a look at Yiping's question. Could we show how L'Hopital rule is used in the graphing problems? Yes, let's do it. So let me go to section 4.5 and I'll grab a problem here where L'Hopital's rule would be necessary. Come down in here. So remember what L'Hopital's rule is for, right? L'Hopital's rule is a tool for taking limits, specifically limits that are kind of not obvious. So if I look at problem number 52 down here, we're not going to go through the whole problem because these take forever, but okay, so I've written it this way. I said, how do we use L'Hopital's rule in graphing the curve y equals ln x over x squared? To solve the full problem as it's stated in section 4.5, we would first find any intercepts, asymptotes for this function. Then we would take the first derivative, make a number line to find where we're increasing and decreasing mins and maxes. Take the second derivative, make a number line to find where we're concave up, concave down, and any inflection points. And at the step where you're finding asymptotes, you would want to use L'Hopital's rule here. And really, there's 2 places here where we'd use L'Hopital's rule. So let me switch to purple. We want to find both vertical and horizontal asymptotes. And in that step, we will use L'Hopital's rule. In fact, for both vertical and horizontal asymptotes. So does anybody looking at this, let's start with the vertical asymptotes. Does anybody have an x value where they suspect this thing has vertical asymptotes?
0.
Yeah, so the downstairs here, x squared, that's 0 when x is 0. And it gets worse. The natural log of x tends to negative infinity as x tends to 0. So we suspect VAs at x equals 0. Now, a quick note, the domain here is the open interval 0 to infinity from the natural log, right? If not for the natural log, it would be everything except 0, like 1 over x squared has domain all real numbers except 0. But the natural log can only take positive inputs. So we suspect a vertical asymptote at 0, and my domain is just numbers bigger than 0. So if I want to investigate that suspected vertical asymptote, I should look at the limit as x approaches 0 from the right, because I got to stay in my domain.
I have a question. When do I suppose the x is going to the 0? When do I suppose x is going to infinite?
So we take limits as x goes to infinity when we're looking for horizontal asymptotes. All right, think of horizontal asymptotes as like end behavior. They are the things your function approaches as x gets really, really big in either direction. So the two places where we would use limits to investigate this function would be when you're looking for vertical asymptotes and when you're looking for horizontal asymptotes. Sometimes vertical asymptotes are obvious, right? Like if the bottom is 0 and the top is not doing anything weird, then you can be confident you have a vertical asymptote there. If both the top and the bottom are 0, or both the top and the bottom go to infinity at any particular x value, then you would need to investigate with a limit. Now here, what's actually happening is not that bad, but I still claim it's worth looking at carefully a little bit because both of those functions do something weird at 0. The bottom is equal to 0 when x is 0, which is a problem, and the top is undefined when x is 0, which is a problem. Now here, my first thought was you might need L'Hopital's rule, but I think now that's probably not the case, looking at it a little more carefully, because ln x on its own goes to negative infinity as x goes to 0 from the right. So the top here would be negative infinity. And the bottom here, x squared, goes to 0 as x goes to 0. And since it's an x squared, even if we weren't going to 0 from the right, this would be like a 0 plus. So what is negative infinity, or a very, very large negative number, divided by a very, very small positive number?
A very, very large negative number.
Good. So a large negative divided by a small positive. This is actually not an indeterminate form, right? Infinity over infinity, 0 over 0, those are indeterminate. But if you take a very, very big negative number and you divide it by a very, very small positive number, you get a very, very big negative number. So my function does have a vertical asymptote at x equals 0. And what's it doing? It's diving down to negative infinity as x approaches 0 from the right. So just like the natural log itself, right? This sort of local behavior, the graph of y equals ln x over x squared near x equals 0 looks like the logarithm itself. I can't say what's going on anywhere else, but I can say as we go to 0 from the right, my curve goes to negative infinity. So I've got an arrow going down here. And I don't think there's anywhere else we could run into vertical asymptotes here, right? The logarithm's only problem spot is 0. And this factor downstairs would contribute a vertical asymptote on its own, but only one, and that was also at x equals 0. So this is all the work for vertical asymptotes. Horizontal asymptotes, on the other hand, here we do need to be a little bit careful. So remember, to find horizontal asymptotes, we look at two limits. lim x goes to positive infinity f of x, and lim x goes to negative infinity f of x. This one I can ignore due to the domain.
You only wrote limit x approach 0 plus from the right side. Is it because the logarithm x cannot equal less than 0?
Exactly.
So, okay.
Yeah.
thanks.
So if this was like the logarithm of x squared, or the logarithm of the absolute value of x, I would want to look at both the right limit and the left limit. But because the domain of this function is just 0 to infinity, I cannot approach 0 from the left. Exactly like you said, because of the ln of x, the only numbers I can plug in here are positive numbers. So I don't need to worry about lim x to 0 minus. In other words, normally we would ask, okay, this arrow on the right goes down at that vertical asymptote. What happens on the left? Is there an arrow going up over here or going down over here or something else? Normally we would look at the limit from the right and the limit from the left. But because of my domain here, I know that there's nothing going on here. There is no arrow on the left side of that vertical asymptote because the domain of this function is just these guys.
And with vertical asymptotes, we don't do that as one. We wouldn't do it as one limit as x approaches 0. We would do it as one x approaches 0 from the left and from the right in case they go opposite.
Yeah, it's wise to investigate them from either side.
Okay. Thank you.
Now for my horizontal asymptote, similar thing. Normally we would look at the limit as x goes to positive infinity and the limit as x goes to negative infinity. But again, my domain is just 0 to infinity, so I can't do this, right? This limit is not something we can even talk about for this function because the domain of this function doesn't include anything anywhere near negative infinity. But we do need to look at this guy. So this would be the limit as x goes to positive infinity of the natural log of x divided by x squared. And again, thinking about the graph y equals ln x, just this guy, the top goes to infinity. And downstairs, if you square infinity, you get infinity, right? So this is an infinity over infinity thing. So we're going to use L'Hopital's rule. And L'Hopital's rule says, differentiate the top and differentiate the bottom, and then try to take your limit again. So the derivative of ln x is 1 over x. The derivative of x squared is 2x. And you could actually work with this directly here, but I think it's nice.
0 over infinity.
Yeah, it is. So this is 0 over infinity, but let's just for the sake of doing the algebra, 1 over x divided by 2x is 1 over 2x squared. So this is definitely 0, right? The denominator is going to infinity, which is 0. But you could also, like Sarah says, argue from here that this is 0 over infinity, which is 0. Either one's fine. So we do have a horizontal asymptote. There is a horizontal asymptote. Y goes to 0 as x goes to plus infinity. So then I know my graph. I can fill in the local behavior near the asymptotes as follows. I have an arrow going down over here. And then I have an arrow approaching this either from below or from above. And if I want to know whether I approach my horizontal asymptote, like is this 0 plus or 0 minus, I should imagine plugging some large numbers in here. If I plug like e to the 10 in here, then I get the natural log of e to the 10, which is 10, divided by e to the 10 squared. Definitely that's positive, right? 10 divided by e to the 10 squared. So I will be approaching this guy from above. And from there, we got to figure out what the hell else is going on in here, right? That's the challenge. And that's what you would get from your derivatives and your number lines. But this is the information we get from thinking about asymptotes. And those are the only two places where you would use L'Hopital's rule in a curve sketching problem. So L'Hopital's rule can be useful when you're looking at vertical asymptotes, and it can be useful when you're looking at horizontal asymptotes. It can also be useful when you're looking at other places where a function is undefined. But those are things that you would sniff out as you're looking for vertical asymptotes. Let me see if I can find an example. Wasn't there one involving the inverse sine function somewhere? Maybe not. We can look at 51 really quick. X e to the negative 1 over x, right? Question. So we want to ask, are there any places where this function is undefined? Anywhere we think we might run into vertical asymptote stuff? L'Hopital's rule guaranteed, or well, not guaranteed, but might be useful there. And then you also want to ask about horizontal asymptotes. Is there anywhere that that we might use L'Hopital's rule in that? So the answer to the question is the same, vertical and horizontal asymptotes. Places where this function is undefined, looks like just at 0, right? Right, because you'd have e to the negative 1 over 0. Our domain here is negative infinity to 0, unioned with 0 to infinity. And if we want to know what's going on at 0, is it a hole? Is it a vertical asymptote? Is it something else? Then we would investigate with a limit. And here, I think it's wise to look at both the left and right limits separately. So I can look at the limit as x goes to 0 from the left of f of x, which is limit x goes to 0 from the left, x e to the negative 1 over x. And the first thing we do is just try to plug in sort of naively 0 for x. So if I'm going to 0 from the left, then that x piece would be a 0 minus. And e to the negative 1 over x, as x goes to 0 from the left, 1 over x goes to negative infinity. So this would be like negative infinity. So this is like a 0 times e to the infinity, which is infinity. And that is an indeterminate form. It's an indeterminate plot.
How do you know if the 1 over x is going to the negative infinite? Because if I plot 0 in the x, you only 1 over 0, so it's going to infinite. How do you know it's negative infinite?
So I'm thinking about the graph of 1 over x. 1 over x itself looks like this, right? This is a curve we know well. So as we come in towards 0 from the left, 1 over x goes down to negative infinity. Another way to do it is to just think about the reciprocal of a small negative number, right? If you take 1 and you divide it by a very small negative number, you get a very large negative number. So this piece on its own, 1 over x, goes to negative infinity. As x goes to 0 from the left. Either way, I prefer to think about the graph. That's what works well for me. But that logic of 1 divided by a very small negative number should be a very large negative number will also get you this negative infinity. From here, because this is an indeterminate product, I would want to rewrite it as lim x to 0 minus e to the negative 1 over x divided by 1 over x. Could do this. Or we could stick the e to the 1 over x downstairs. I like this more though, because when I differentiate the top with the chain rule, I'll get something that cancels with the bottom. So at a glance here, this is now positive infinity over negative infinity, which is an indeterminate ratio. So if I apply L'Hopital's rule, looks like I'm going to need more space to talk about horizontal asymptotes. If I apply L'Hopital's rule, the derivative of the top is e to the negative 1 over x times the derivative of negative 1 over x, which I'll just write as negative 1 over x prime. Because the derivative of the bottom is, well, maybe I'll write about 1 over x prime. And these are more or less going to cancel. But let's go ahead and do the calculation. I don't want to be too lazy here. Make things confusing. So that's e to the negative 1 over x times the derivative of negative 1 over x is positive 1 over x squared. The derivative of positive 1 over x is negative 1 over x squared. And if I bring that negative 1 over x squared back up, we get lim x to 0 minus e to the negative 1 over x times 1 over x squared times negative x squared over 1, cancel. And we're left with lim x to 0 minus. The negative here survives, so I have negative e to the negative 1 over x. And again, the negative 1 over x, so this 1 over x piece is going to go to negative infinity. Negative 1 over x will go to positive infinity. So that's negative e to the infinity, which is negative infinity. So as we approach 0 from the left, this curve is diving down to negative infinity. What about as we approach 0 from the right? This would be lim x to 0 plus x e to the negative 1 over x. And again, I'll kind of lean on my 1 over x graph to help me out here. As x goes to 0 from the right, 1 over x is going to positive infinity. So this
I was wondering how negative e to the negative 1 over x becomes negative e to the infinity.
Let me ask, so where are we looking here? How negative e to the negative 1 over x. So this negative 1 over x, so 1 over x on its own, this is going to go to negative infinity as x goes to 0 minus. So this is negative infinity. Now you can think of it like that if you like. So negative 1 over x is going to positive infinity. So it's really the same logic I applied up here. That's why I wasn't as verbose about it. It's the same thing we did here to say that this is infinity.
Okay, thank you.
Yeah, no problem. All right, so let's come back down
Other
here.
question.
Oh, sure, go ahead.
Sorry, a negative number, if it's going to the power of positive infinity, why is it still holding on to, what's making it negative still?
The negative is outside. So this, that's a good question. And this is something that I have seen people get a little tricked up on in the past. It's like this.
Okay. Oh, that makes sense. Cool.
Yeah. So anytime you have a negative number being raised to a power, we must use parentheses. And if you see it without parentheses, it means the negative is outside the power. All right. So coming back, limit 0 plus of the x piece here is 0 plus. 1 over x, as x goes to 0 plus, is going to positive infinity. So negative 1 over x is going to negative infinity. So this is e to the negative infinity. So I have 0 plus times e to the negative infinity. What is e to the negative infinity?
0.
Mhm. So there's no need for any L'Hopital's rule here. This is not an indeterminate form. I get 0 times 0, which is 0. And this is pretty fascinating behavior. There are not a lot of functions we've played with that do this. You have a vertical asymptote at x equals 0, but you only blow up on one side of it. You're defined on both sides of it, but on one side, you have a finite limit. On the other side, you have an infinite limit. So in other words, the behavior near 0 here, as x goes to 0 from the left, f of x goes to negative infinity. And as x goes to 0 from the right, f of x goes to 0. And it's 0 plus, right? This is always positive. So we're coming down to 0 on the right, and we're going down to negative infinity on the left. In other words, if I want to sketch the local behavior near my vertical asymptote, I have a VA at x equals 0. That's what we've just discovered. On the left-hand side, we're going down to negative infinity. On the right-hand side, we're approaching 0, but we know that this function is undefined at 0, so we have a hole. So we're doing something like this. This is what the local behavior near 0 is. Neat, right? I know that this is coming in from above rather than from below because this is a plus. And I know that we're going down on the left because as x goes to 0 from the left, f of x goes down to negative infinity. So this is kind of weird behavior near 0. We don't see this sort of stuff a lot, but it's not that hard to figure out. The other place we'd maybe use L'Hopital's rule here is with horizontal asymptotes. So if I take a peek at the limit x to negative infinity, f of x, let's see what that is. That's limit x to negative infinity, x e to the negative 1 over x. This x piece is definitely going to negative infinity. And as x goes to negative infinity, 1 over x is going to 0 in a negative fashion, right? Again, just thinking about the graph of 1 over x. So this would be e to the negative 0 minus, or just e to the 0. So that's negative infinity times 1, which is negative infinity. So no horizontal asymptote on the left. As we go way, way out over here, we're just going down. On the other hand, the limit as x goes to positive infinity of f of x is the limit x goes to positive infinity, x e to the negative 1 over x. Here, the x piece is going to positive infinity. 1 over x is going to 0 again, right? So negative 0 is still 0. So this is positive infinity. So my end behavior, if you want, kind of all the asymptotic behavior. We do have a vertical asymptote at x equals 0, which we approach going down on the left, and we do not approach at all from the right. We just kind of come in here doing something like this. Who knows what else, but something like this. My end behavior on the left, as I run out towards negative infinity, is going down. So I've got a, just an arrow over here going down. Who knows what's going on in here? Maybe something like this. And on the right, as x goes off to positive infinity, we're going up to positive infinity. So my end behavior over here is something like this. And then to fill in all the bits between here, again, that's the work of the number lines. Let's take a quick peek at this one. This is not a graph I know off the top of my head. Interesting. Yeah, we weren't too far off those kind of random guesses. So the actual graph here, and you would discover this by playing around with your number lines, looks something like that over here. And I don't see if we, are we ever decreasing in here? It doesn't look like it. No, just blowing up. Something like this. More or less. I guess it's a little bit closer to like this. Well, that's the vibe. And in particular, we know that we are approaching 0 from above on the right and approaching negative infinity as we come into 0 from the left. There are no horizontal asymptotes, and the end behavior on the left is down, the end behavior on the right is up. Pretty cool. Pretty cool. All right, I think that's enough talk of L'Hopital's rule as it applies to curve sketching. There are other problems like this, like if I ask you to graph sine x over x, that's a great example of a problem where you could use L'Hopital's rule at 0. I think one of the examples in here somewhere has to do with the inverse sine function, and that is another example where L'Hopital's rule could be useful. Maybe not, maybe I'm thinking of a different section. Yeah. I said we should do some related rate stuff, right? Let's get back to a little implicit differentiation, related rates work before we run out of time. So, inverse trig functions, always fun. I think I've told you I have a deep love for the inverse tangent function. Let's take a look at number 17. Arctan is our friend. We're given the inverse tangent of x squared times y. And we're told that that's equal to x plus xy squared. I want to find dy dx. So tan inverse of x squared y equals x plus xy squared. And remember here, if you're looking for dy dx, the implicit assumption is that y is a function of x. There's a beautiful theorem that is just beyond the scope of this class called the implicit function theorem. It's kind of one of a two-part theorem, implicit function theorem and inverse function theorem, that discuss when a curve can be thought of as locally a function. So the classic example here of the circle fails the vertical line test, right? But if you just look at one little part of the circle, as long as you stay away from this point and this point, you can think of any little part of the circle as being the graph of a function, right? For example, just the bold part here near the point A, if you delete everything except for that, that does pass the vertical line test. So we can implicitly think of that as a function. And that's what I mean when I say this. So even though this whole curve may not give you a function, you can look at any individual part of it and think of that as a function. All right, the game here is to apply the operator. I'm looking for dy dx, so I need to apply the differential operator ddx to both sides. On the left-hand side, I have ddx of the inverse tangent of x squared times y. And on the right-hand side, I have ddx of x plus xy squared. And on both sides, we need to be quite careful with the chain rule, product rule, all that stuff. Recall that the derivative of the inverse tangent of u is 1 over 1 plus u squared times u primed. And if u is like a function of x, chain rule stuff. If you're differentiating with respect to u, you just get 1 over 1 plus u squared. But here I do have a more complicated thing inside my arctan. So the left-hand side is going to be 1 over 1 plus this inside x squared times y all squared times, excuse me, the derivative of x squared y. And here with the prime, I mean derivative with respect to x. On the right-hand side, x differentiates to 1, and then plus, I need a product rule here. This would be 1 times y squared plus x times 2y y prime. So again, we're differentiating implicitly. Is everybody comfortable with the second purple line? Are there any questions so far? Okay. On the left-hand side, we're going to need a product rule for this, and we're going to need to differentiate implicitly there. This object, 1 over 1 plus, I'll write it as x to the 4y squared, because that's what x squared y all squared is. Here, when I differentiate x squared y with respect to x, I'll get, by the product rule, 2x times y plus x squared y prime. And on the right-hand side, not much more to do now. That's just 1 plus y squared plus 2x y prime. And I want dy dx. Remember, dy dx, this is y prime. So I want to solve this equation for y prime. And it's a little nasty. It's a little nasty. Any ideas how I could start solving this for y prime?
All the y primes need to be on one side by themselves.
Yeah, we want to get every term that has a y prime on one side and every term that doesn't have a y prime away from that guy. There's a bit of a challenge here, and it's on the left. I've got this big fraction, which needs to be distributed over these. So in order to start isolating the y prime from this piece, I actually need to distribute this across these. So I would begin by rewriting my left-hand side as 2xy over 1 plus x to the 4y squared plus x squared over 1 plus x to the 4y squared times y prime. So I'm just leaving the y prime. I could put the y prime upstairs here if I wanted to, but I'm leaving it there to emphasize that I'm going to factor this piece out eventually or get rid of it. My right-hand side is still the same. I have 1 plus y squared plus 2x y prime. Sorry, I know my y's sometimes look a little g-ish. So this term has a y prime, and this term has a y prime. I'll bring this over here. This term and these terms do not have a y prime, so I'll put that over there. We'll get x squared divided by 1 plus x to the 4y squared y prime minus 2x y prime equals 1 plus y squared minus 2xy divided by 1 plus x to the 4y squared. And now on the left-hand side, I can factor out y prime. And what's left is x squared over 1 plus x to the 4y squared minus 2xy equals 1 plus y squared minus 2xy over 1 plus x to the 4y squared. And to finish things up, I need to divide both sides by the bracketed term. So this is going to be a pretty nasty looking expression. We can try to clean it up some from there, but you could officially declare victory at this line, y prime equals 1 plus y squared minus 2xy divided by 1 plus x to the 4y squared, all divided by x squared over 1 plus x to the 4y squared minus 2xy. So technically we have solved the problem at this step. Yeah, I'll zoom back out and go up in a second. Now, suppose you had to do something with this, like God forbid, set this equal to 0, right? If you're looking for horizontal tangent lines or something like that. Can anybody suggest a good first step to cleaning this up?
There are common denominators you can find in the top and the bottom to simplify all of it.
It's true, and more is true. The common denominator between the two pieces downstairs and the common denominator between the two pieces upstairs are the same, right? It would be the 1 plus x to the 4y squared. So if I wanted to, instead of going through that process, I could multiply top and bottom by 1 plus x to the 4y squared. And when I distribute the orange piece upstairs, when this piece smacks this piece, I'll just get the 2xy. When it smacks this thing, I'll get something nasty, but whatever. At least it's a polynomial. When this piece smacks this piece, I'll just get x squared. And I will have 2xy times this thing again, but at least that's a polynomial. So in an ugly world where you have to do something with this, I would rewrite it like this. That would be a good first step towards cleaning this up and doing stuff with it. You could then distribute, right? FOIL this, distribute this, see if any like terms combine. I wouldn't expect it to, but I think this is about as nice an expression for the derivative here as anybody could ask you for. All right, there was a request to come back a few steps, so let me do that. I'll zoom out and bring it down a little. I think that was our first step where we differentiated, right? Yeah, so here. Is this what we wanted to see? Okay, I'll hold here for a few seconds. We have about 10 minutes left. What do we want to see in those remaining 10 minutes? We want a related rates problem, something else?
Either related rates or that last section.
Oh yeah, we haven't done any optimization yet today, have we?
Yeah.
Let's do some optimization. 5 more seconds. Okay, here we go. What a fun one. Something physicsy that we can do in 10 minutes. So that's fun. This is actually a classic example, and we haven't done one of these yet. Let's do one of these. So 1200 square centimeters of material is going to be used to make a box. The box is going to have a square base and it's open on the top. We want to find the maximal volume of such a box. And notice here, they didn't, one of the things you want to pay careful attention to on these problems that might seem a little silly is exactly what they're asking for. They didn't ask for the dimensions of the largest volume box. They asked just what is the largest volume. So let me get the important stuff written down. Find the max volume of a box with square base and open top made with 1200 cm squared material. All right, here we are. I'm going to find the maximum volume of a box with a square base and an open top that can be made out of 1200 square centimeters of material.
Is it safe to say we're working with a cube? Like, do we have to take square very seriously that all the sides have to be equal?
Just the base is square. So let's start by drawing a picture. Certainly that's the move here. I am not an artist, and I don't expect you guys to be artists, which is why we like to label things. So here is the base of my box. If this is going to be a square, then each of these side lengths I'll just call X. They're all the same. And then the height of my box is allowed to be whatever I want. Yes, baby, what's up? I'm teaching.
Sorry, do I need to put?
Sorry, wife got a flat tire. Okay. So the base of the box is square, and the height of the box I'll call Y. The top of the box is open. We want to maximize the volume. And that volume, V, is length times width times height, right? So that's X squared times Y. The other restriction, the constraint here, is the surface area. And the surface area you have to think about a little bit carefully. Remember, the top of the box is open. It's like a shoebox with the top off. So there's stuff on every one of these sides except for the top. So the base is X squared, I'll call this S. The base is X squared. I need X squared centimeters of material to make the base. And then I've got 1, 2, 3, 4 sides. Each of those sides has dimensions X times Y. So this is plus 4XY. If I want to maximize this volume, the slick way to do this is to plug in 1200 for my surface area, solve this for Y, plug that in here, then differentiate. The other day, somebody asked, could you differentiate this implicitly, assuming Y is a function of X? Yes, you could, but then you would need to calculate dy dx separately somewhere. It's very easy to get confused. So I say, rewrite your the thing you're trying to optimize, maximize, or minimize as a function of a single variable first using the constraint. So I know that 1200 is equal to x squared plus 4xy. I could solve this for x or for y, but it's certainly easier to solve for y. As a function of y, it's linear. As a function of x, it's quadratic. So let's solve for y. I get 1200 minus x squared over 4x equals y. And then plug that in.
Excuse me?
Yes.
Wouldn't it, I thought, wouldn't the surface area be 2x squared because there's the top and the bottom?
Oh, no, remember the top is open.
Oh, it's open. Okay.
If there was a top on this box, then you would be correct, but they said the top is open here. So now my volume is x squared times y, which is 1200 minus x squared divided by 4x. And I can clean that up a little bit. I'll write it as v of x to emphasize that it is now a function of the single variable x. I can cancel the x downstairs with the x out front. I can pop out a 1/4. So I'll have 1/4 x times 1200 minus x squared. And I can further simplify this to 1/4 times 1200x minus x cubed, which is the nicer form to differentiate, right? Because this does not require a product rule, whereas this would. V prime then. The 1/4 is a constant multiple. He just comes along for the ride. The derivative of 1200x is 1200 minus the derivative of x cubed is 3x squared. I can factor out a 3, giving me 3/4 400 minus x squared. And I can further factor this as a difference of squares. That's 3/4 times, let's see, 400 is 420 squared. Yeah, so that's 20 minus x times 20 plus x, like so. So the critical numbers for the function v, places where v prime is 0 or undefined, when x is 20 or negative 20, and v prime of x is never undefined. We didn't make any statements about the domain here, and this is kind of similar to the oil can problem, where because it's the surface area that's constrained. Oh, actually, let me see. No, we might be able to come up with a clear constraint. Definitely x and y both need to be positive because they are distances. And I think coming up with a domain here is actually going to be a little bit tricky, saying that you need this thing to not exceed 1200. Definitely x has to run from 0 up to something, but exactly what, I guess it would be the square root of 1200. It's not nice, but we can, our goal here is to find a min or a max anyway. So we really don't need to stress too much about that, because at either of the extremes, if x is 0, obviously the volume is 0. And if you make x as large as possible, then y would be forced to be 0, right? So if you made x the square root of 1200, then y would be 0. So definitely mins at both endpoints.
I cannot understand why v prime is undefined.
Oh, it's never undefined.
Okay.
Yeah, so v prime is a polynomial, right? And polynomials have domain all real numbers. And we could say, here, I'll go ahead and state it. We want to maximize over the x interval 0 up to the square root of 1200, just for completeness. But we really don't need this information in order to solve the problem. Because clearly at either endpoint, you're looking at a min, right? The volume would be 0 at either of those endpoints. Also, the -20 is not terribly interesting, is it? Right? I can't have a negative side length. So we put 0 over here, 20 over here, and the square root of 1200 over here. I'll make my number line for V prime. I'm not interested in.
How did you get the square root 1200?
So I'm imagining that I put all, I'm trying to find the x values that I could possibly use in this function, right? And the idea is thinking about the physical situation. If I put no material into the base, I put all the material into the sides, then x is 0. So that's where the 0 comes from. And if I put all the material into the base and put no material into the sides, then that would mean I'd have to have a 1200 centimeters square base, right? The area of the base would be 1200 cm squared, which means each side length is the square root of 1200. So this is like y equals 0, no height. I'm sorry, no, this is all height. And this is like all base. So if we're putting all the material into the base, making the height as small as possible, then that base would be square root of 1200 times square root of 1200 in length. And if we're putting all the material into the sides, putting no material into the base, then the base would have side length 0. But again, you really don't need this information to solve the problem because we have our theorem, which says if you're always increasing to the left and always decreasing to the right, then this has to be an absolute max. And that's what we're going to find here. So I'm not interested in any of this stuff. This is outside the domain, outside the domain. We can test x equals 1 in here, in this left region. V prime of 1 is, let's do it here, 1/4 times 1200 minus 3.
So 20 is a critical number. You just put the end point in the end point and the critical number, get the point test.
Correct. Yep, correct. So I put the 0 and the square root of 1200 here just to remind myself what would be valid test points. 0 is not a valid test point because it's not in my domain. Square root of 1200 is not a valid test point because it's not in my domain. It's just a nice way to remind ourselves what we're working with. And then I choose to test x equals 1 because that is a point from this region that's easy to work with. 1/4 times 1200 minus 3 would be 1/4 times 1197, which is definitely positive. That's all I care about. So we're positive. Our derivative is positive everywhere in here. And I could test x equals 21 here. And I think there it'll be easier to plug into this. V prime of 21 would be 3/4 times -1 times 41, which is definitely negative, right? Positive times positive is definitely negative. So this is a minus here. So since we're increasing everywhere to the left of 20 and decreasing everywhere to the right of 20, x equals 20 maximizes the function v of x. Now, again, remember what they asked for. They didn't ask for the dimensions that maximize the volume. They asked us, what is the max volume? So the max volume is V of 20. right? The volume when you plug in 20 for x, which is probably easiest to do here, or maybe here. Yeah, let's do it there. So that's 1/4 times 20 times 1200 minus 20 squared. 1/4 times 20 is 5. 1200 minus 20 squared is 1200 minus 400. So this is 5 times 800, which is 3200. Is that correct? And the volume here is measured in centimeters cubed. I'm sorry, that's not correct. That would be 4 times 800. 5 times 800 is 4,000, right? And the units are cm cubed. All right, so I'll leave it here for today. Monday of next week, we are going to do a little bit more review. Please think about what problems you would like to talk about on Monday. We can talk about study guide problems, but I would prefer to kind of stay away from those. Those are things where I want to see what you guys are doing so I can give you more useful feedback. But if there's a study guide problem where you're absolutely dead, then we can talk about it. Definitely homework problems are totally fair game. Natasha asked, do we need to know the derivatives of inverse trig functions? Absolutely, yeah. Not the inverse hyperbolic trig functions, but the regular inverse trig functions, yes, very much so. Just like on that implicit differentiation problem where we used the derivative of the inverse tangent function. You need to make sure you know the derivatives of the inverse sine function, inverse cosine function, inverse tangent function, at least. I could, in theory, ask you about inverse secant, cosecant, cotangent, but I won't. So I'm comfortable telling you that off the bat. Arc sine, arc cosine, arc tangent, definitely you need to know those. Yeah, studying a little bit together over the weekend sounds like a good idea. Definitely encourage you guys to do that. I'm going to get running for now. Please work hard on the homework, study guides. If you're stuck on anything, you know how to ask for help. I do have an office hour this afternoon from 1 to 2 p.m. I will be proctoring a makeup test for some people there. So if you want to come to the office hour this afternoon and talk, we can. Just be aware that we're going to have to be like a little bit quiet because I'll have people working on makeup tests. Oh. Yeah, and if you guys want to swap any contact information, that's not a bad idea. I'll leave the meeting up for a second here so y'all can do that. Is there anything else anybody would like to ask before we get moving? All right, everybody was able to swap all the contact info they want? Yeah, check out the Discord. Did I give you guys a fresh invite link? These things just keep expiring. Bye, baby. Here, just in case anybody has lost it or in case the link has expired again, because I know it does expire often. Let me get you a fresh invite link. The Discord. There we go. All right, so maybe copy paste that link somewhere safe. And it should work for about a week. Oh, sorry, that just went to Sarah, didn't it? I'm sorry. Here we go. Alrighty then, I'm going to go ahead and end the meeting. I hope you guys have a lovely rest of your day. If you need to talk to me, you know how. And I will see y'all on Monday.